Good day, everybody. I am here today to discuss to you about the particular functions, the particular concepts and aspects that you can commonly associate rectilinear motion with. So we'll discuss what is rectilinear motion, what is the definition of rectilinear motion, and how rectilinear motion can be applied to everyday things, and what examples can be derived from this said concept. Now that was a great mouthful of words that I just made out of my mind, so I'm feeling really smart right now. Anyways, we have a unit test tomorrow. I'm sure as hell I'm gonna fail that, so I'm gonna try my best to discuss to you in a very entertaining and simple way so that we can understand the concept of rectilinear motion itself. So without any further ado, let us start this discussion with the definition of rectilinear motion. So what is rectilinear motion? So in our discussions of rectilinear motion refers to the motion of a particle or an object along a straight line. This type of motion is one of the simplest forms of motions in physics, as the path followed by the object is linear. The key parameters that describe rectilinear motion are displacement, velocity, and acceleration. Now, that was a mouthful, so let us take it slow. So what is rectilinear motion? So, as I've said, this simply is the motion of a particle or an object along a straight line. So whether it be going in a straight line left or right, whether be it up or down, if it is in a straight line, it shall be considered a rectilinear motion. Now, what are these key parameters that describe rectilinear motion? Or what are these concepts that coincide with the very definition of rectilinear motion? So how does rectilinear motion work? So first of all, in order to describe the nature of rectilinear motion, we'll have to first be familiar with the three parameters that describe the essentially the essence of rectilinear motion. So first is displacement. Keep that in mind. We'll go back on that. Displacement. So displacement is its definition: the change in position of an object in a particular direction. It is a vector quantity and has both magnitude and direction. So what displacement simply means is that it is a measure of the direction in which an object changes a position in. So basically, if the object changes in position, if the object changes in position in a particular direction, you'd consider that as displacement. You could measure it, which is why it's called a vector quantity, and it has both magnitude and direction. So the most important thing you must remember when we deal with displacement is that you remember it is the direction, that is also the change in position of an object. Now we go to another concept, which is velocity. So what is velocity? So velocity is the rate of change of displacement with time. It is also a vector quantity, and it can be constant, so it should be a uniform motion or a non-uniform motion, or also known as a variable. So velocity, in other words, is the rate of how fast the change of displacement something is with time. So basically, you measure the change of displacement with time, and you call that velocity. And with its measurement of time, we can call velocity a vector quantity, which means it can be measured, and it is and can be a constant and a variable. So now that we've discussed displacement and velocity, the final key parameter that describes rectilinear motion is acceleration. Now, what is acceleration? It's the rate of change of velocity with time. So velocity is the rate of change of displacement with time. Acceleration is the rate of change of velocity with time. So when the velocity of an object increases, the acceleration is positive. So when it increases, it is positive. And when it decreases, deceleration occurs, and that is what we call a negative process. So essentially, in terms of acceleration, all you need to remember is that acceleration is the rate of change of velocity with time. So basically, essentially, how fast it is, how fast the change of velocity is with time. And then, when it is positive, we would call that process acceleration. And when it decreases, we call that process deceleration. Now these are the important values that we should consider in terms of rectilinear motion. And there are two types of rectilinear motion, essentially, as far as I can remember. So the first one is uniform rectilinear motion. Now this was not discussed in class, but I'm just explaining it to you so that when you encounter a problem in the future, you can essentially differentiate what are the different classifications of rectilinear motion. Uniform rectilinear motion and non-uniform rectilinear motion. So what are these two things? So first of all, uniform rectilinear motion basically occurs when an object moves with constant velocity, which means it is constant, never changing, and therefore it stays the same way. So basically, it means zero acceleration. Now, essentially, non-uniform rectilinear motion is just the opposite of this process, which means that an object's velocity changes over time. Basically saying that it experiences acceleration, it goes faster. So uniform is just, it's fast in the same way, never changing. And then non-uniform rectilinear motion basically means that it goes fast and it will go faster. Now, to recap, once again, rectilinear motion is simply the motion of a particle or an object along a straight line. The key three parameters that describe this said movement, this said motion, this said rectilinear motion, is displacement, the change in position of an object in a particular direction. Velocity is the rate of change of displacement with time, and acceleration is the rate of change of velocity with time. Now, always remember, rectilinear motion can be classified as uniform rectilinear motion and non-uniform rectilinear motion. Uniform rectilinear motion refers to how fast an object is in the same way. In other words, it's never changing, same pace, so it's always going to be fast, and it will just be fast. It will stay that same way. And the non-uniform rectilinear motion is when it's fast, then it goes faster. So basically, the object's velocity changes over time. It's meaning to say it just experiences acceleration. So basically, uniform is zero acceleration, non-uniform is experiencing acceleration. Now, we'll see what the examples of uniform and non-uniform examples. So first, uniform rectilinear motion. You can classify a car traveling on a straight road at a constant speed of 60 kilometers per hour. Now, when you hear the word constant speed, that basically means that the displacement increases linearly with time. In other words, it's heading in the same direction slowly and slowly at the same pace. It will take time, but it will arrive at its destination, which is why it's considered a factor of displacement. Velocity remains constant, which means essentially that acceleration is zero. That means that the vehicle is constantly at a pace of 60 kilometers per hour and it does not plan to accelerate. Meaning to say that if it does not accelerate and it stays the same velocity, remains constant. If it remains the same constant velocity, that means the acceleration is zero, and thus meaning to say this is an example of a uniform rectilinear motion. In other words, the car is just traveling to its destination at a constant speed of 60 kilometers per hour, never changing, never going faster, always staying the same. Now, basically, an example of non-uniform rectilinear motion is just this example, but we'll just accelerate the car. So basically, a car overtakes that car that we had an example earlier at 60 kilometers per hour. So meaning to say, if the car overtakes a car that we had used an example earlier, which was traveling at a constant of 60 kilometers per hour, what this essentially means is that this car over here is traveling at 60, and the car that overtook this car that is moving at 60 kilometers per hour has a greater accelerated value, which means the displacement increases non-linearly with time. It doesn't travel in a straight way anymore because the man overtook the 60 kilometer per hour car, so it would go ahead. If you travel in a straight line, just straight while accelerating, if then there is an obstacle in front of you, you will die, you will crash the car. So basically, this man went from here and then overtook him, so which means that his speed exists, and his speed basically is faster than 60 kilometers per hour, which means he experienced acceleration. It has a positive acceleration, it's constant acceleration, and then velocity increases over time. So basically, what we just need to remember is, if it's constant velocity, acceleration zero, means it's a uniform rectilinear motion, and then if it's constantly accelerating, the velocity increases with time, and then the displacement increases non-linearly, which means it's going zigzag with time. That means it's a non-uniform application of rectilinear motion. Now, we'll have a example. So I'll just pick a simple example for us to discuss. So we'll go with the constant acceleration of the car. So our problem set is a car starts from rest and accelerates uniformly at 2 meters per second square along a straight road. What is the car's velocity after 10 seconds? So what we're trying to find here is how far the car traveled in this time of 10 seconds at an acceleration, a uniform acceleration of 2 meters per second square. So our given is our initial velocity. So we'll just VI that is at 0 meters per second squared because it was at rest, and then our acceleration was at 2 meters per second squared, while our time was 10 seconds. So what we're gonna do is we'll have the formula for final velocity. So final velocity, trying to figure that out. Velocity, so it's going to be V equals VI plus AT. So, and the formula that I was given, that I used for reference, the initial velocity symbol was U, but in order to make it easier for myself, I'll just have to use the VI, the symbol that we use for initial velocity in school. So first, this is our first step. So final velocity, velocity equals 0. Okay, that's our initial velocity, and then we times our acceleration and time. So that's going to be 2 ms squared times 10 seconds equals 20 meters per second squared. So what we're going to do is just we figure out the displacement as well, which is S equals VI. So instead of using U, we'll just use VI again, and then time plus 1/2 acceleration and time squared. So what we're basically gonna do here is we're just going to fill in the steps, and we're going to have S equals 0 plus 1/2 times 2 meters per second squared times 10 seconds, which was our time, squared. So when we take that into consideration, the answer is going to be, allow me to calculate, okay, so we're going to answer that. Our answer is going to be S equals 1/2 times 2 times 100 equals 100 meters. So the car's velocity after 10 seconds is 20 meters per second, and has traveled 100 meters. Essentially, this equation is just trying to figure out how far the car has traveled in this time. And so with this process of figuring out the factors that we have been given, so basically we use the initial velocity alongside our acceleration and our time to see how fast our displacement occurred, in which we have received an answer, in which I have solved the answer, and the answer is 100 meters. That's how far it traveled in a span of a few seconds, basically. So the car's velocity after 10 seconds is 20 meters per second squared, and it has traveled 100 meters. So the answer to the question of how far has the car traveled in the time of 10 seconds, well, let's 100 meters. And that's basically it. I'm gonna divide this video into fractions basically. So 10 minutes for the discussion of the principles of rectilinear motion and 10 minutes for the discussion of the problem set. So anyways, thank you very much.